will look at the electromagnetism section of the physics syllabus. So a magnetic field exists around magnets as well as a current carrying conductor. So when we look at magnets, a magnetic field exists around a magnet. It's a region where another pole will experience a force. Now we know from magnets that like poles react, so two south poles will repel and a north pole will repel, whereas unlike poles attract. So if you had a north and a south pole, you will have attraction or force of attraction between the two poles. If we look at common magnetic materials, we have copper and aluminium. If we look at how these magnetic materials work, your metals become magnetized. The unpaired electrons in the metal align in their preferred direction, leading to a north pole and a south pole, and therefore a magnetic field. So a hard ferromagnetic metal is one which produces a permanent magnet, and a soft ferromagnetic metal is a metal that will magnetize near a permanent magnet but lose it when it is removed from the field that surrounds the permanent magnet, or the hard ferromagnetic metal. If you look at the field around a magnet, if you have two north poles, you will have the field lines moving away from the north as field lines go from the north pole to the south pole. And when you have two like poles, you will have a neutral point which will shift depending on the strength of the magnets and always be further away from the magnet with greater strength. When you have a magnet with a north and a south pole, you simply have your field lines perpendicular out of your magnet moving from your north to your south pole, and they are closer together near the magnet because the field is stronger, and further apart, further away from the magnet, because your field is weaker. Your magnetic field is weaker at this point. So as I've said, your field lines are drawn from north to south, and north to south would be around, and they never cross, they're always perpendicular, and they're drawn close for a stronger field, as you can see over here, and further apart for a weaker field. When you look at magnetic fields around a straight conductor, when you have an electric current in a conductor, this will produce a magnetic field. So the magnitude of the current affects the magnetic field. If you had a wire such as we can see here, where your current is moving upwards, you use your right-hand rule, which most of you will know is the right-hand rule, to work out your direction of your magnetic field as well as the direction of the current. So you would hold the conductor with your right hand, you would point your thumb in the direction of the current, so in this case your thumb will be up and you will hold the wire, and the direction in which your fingers curl is the direction of the magnetic field. So you can see if you hold this conductor with your thumb upwards, your fingers point towards you, and therefore as you curl your fingers, that is the direction of the magnetic field, as we can see over here. You must remember, sometimes they will confuse you and say that your electron movement is up or your electron movement is down. You must know that you are looking for conventional current, and your conventional current direction is always opposite to your electron movement. If we look at an example such as this one, where we have a current carrying conductor over here, our current is moving right. If we use the right-hand rule, we grab the conductor with our thumb pointing to the right because our current is moving right, and we can see that our fingers curl over the top and towards us. We can see this here as these symbols are an indication of the field moving towards us, and these are an indication that the field is moving away from us, and therefore we can see there's a movement like this around the conductor. When we look at the magnetic field around an electric current in a coil, it works the same way as it would in a straight conductor. However, we now have a magnified field in the center. A single coil has a magnetic field, as we see over here, where your current is moving around here, up and left. We use the right-hand rule to put our thumb up. We grab it on the right over here, and we can see that the current will move towards us over here and away from us on this side. And it will do the same thing all the way around. If we grab it over here, we point our thumb down and we can see it's moving away from us over here and towards us over here. Now, when many coils are wound in a cylindrical way, it is called a solenoid. And if we were to put a number of coils together, we will get this over here. We get uniform field lines moving from south to north in the middle of the solenoid. That is important to note. Normally your field lines go from north to south, but in a solenoid, they will always go from south to north. On the outside of your solenoid, they will always go from north to south, and that is simply explained by your looking at a single coil and putting them all together. We can see that if we have our current going in here and we use our right hand rule, we can see it on the inside. It is always moving this way, which is from south to north. So as I've said, your field lines from south to north in your solenoid and from north to south outside your solenoid. We can use our right hand solenoid rule. So we hold the coil in our right hand. If you grab this coil over here in your right hand, your fingers curl in the direction of the conventional current. So you grab it and your fingers point outwards because your conventional current is flowing outwards, and your thumb will point to the North Pole. As we can see, our thumb points up because the current is flowing outwards, and therefore our thumb points to the North Pole, which is at the top. When a soft ferromagnetic metal is put in the solenoid, then an electromagnet is produced. This forms the core of the solenoid. So when current flows through the coil, the magnetic field causes the domains in the core, which is the soft ferromagnetic metal, to align, and this increases the strength of the field. As we can see here, when there's no current, they are not aligned. When there is a current, all of the domains in the core are aligned, and therefore this strengthens the strength of the electromagnet. Your magnetic field, important thing to look at is magnetic field strength, which is also called your magnetic flux density. Now we measure this, the size of the electromagnetic force is investigated using a scale. So we have a current carrying conductor over here in which the current is moving away from us. So we point our thumb away from us and we can see that our fingers curl from left to right, and we know that our magnetic field is then moving like this around our conductor. We have two magnets north to south, so our fields are moving from left to right. Therefore, we can see that at the bottom over here, our field on our conductor is moving right to left, and our magnets are moving left to right. Therefore, they cancel on the bottom. They are moving in opposite directions. Whereas on the top here, our field around our conductor is moving from left to right, and our magnets are also moving from left to right. Therefore, they interact and they strengthen the field on top. So you can see the bottom half cancels out because they act in opposite directions, so these cancel out, and we get an increased force on the top of the wire, which causes the wire to be pushed down, and therefore we have a force downwards on the wire. Now, in order to increase that force, we can increase the current in the wire, therefore increasing the magnetic field around the wire. We can use a stronger magnetic field, therefore increasing the field between the two magnets. We can use a longer length of wire, therefore increasing our amount of interaction, or we must use an angle of 90 degrees. Now, to explain that angle of 90 degrees and how that interacts, we must look at a drawing such as this. When we have an angle of 90 degrees between our conductor and our magnetic field between our magnets, we have max interaction with our magnetic field. Whereas if we have an angle smaller than 90 degrees, only the perpendicular component of our conductor's magnetic field will affect or interact with the magnetic field of the magnet, and therefore our interaction is smaller. When we look at our field strength, which is the force on the wire, this F is the force experienced by the wire, we calculate it using our flux density, B, which is the strength of the magnet, times by our I, which is the current flowing through the wire, times by the length in meters of the wire, times by the sine of the angle made between the wire and the magnetic field between the magnets. So as we can see over here, this is now a further explanation on the angle. Only the perpendicular component will interact with the field, and the parallel component has no effect. So we can see that this component over here would have no effect on the force as it moves with the magnetic field, and therefore has no effect on the wire. This is why we get the greatest interaction when we are completely perpendicular at 90 degrees to our magnetic field lines. And this gives rise to the motor effect. If we have two magnets north and south and we have a wire with a magnetic field, we use our right hand rule to work out that it is flowing like that. We have an interaction at the top. We therefore have a force pushing down on the wire. The magnetic field produced by the current in the conductor interacts with the magnetic field of the magnets. The conductor must be at 90 degrees to the field lines. You said must always be at 90 degrees to our field lines in order to get the maximum force. As we can see here, if our conductor is parallel, there's no force, so this would be pointless. Then we use our Fleming's left-hand motor rule to work out the direction of the force. Our index finger on our left hand is the magnetic field between the magnets. Our middle finger is the current, so we simply point our index finger, in this case from left to right, our middle finger away from us, and we can see that our thumb, which is indicative of the force, points down, and therefore we know the force on the wire is down. Now, the motor effect is how we produce electric motors. So electric motors, you must know, convert electrical energy into mechanical energy. So as we can see over here, we have current moving away from us in a wire. So we have a magnetic field moving like this. We use our right-hand rule to work that out. Therefore, we have an interaction on the top. Over here, we have current moving towards us. Therefore, we have it moving this way using our right-hand rule and an interaction on the bottom. This causes an upward force on the right and a downward force on the left, causing these two and a motion to move anti-clockwise. B moves to position A, and A moves to position B. You must always remember that your current flows from positive to negative if you are ever given it in terms of positives and negatives and not in terms of the direction of flow of current. Now we can see once this has happened, we have current moving away from us over here, leading to a anti-clockwise movement of the magnetic field and an interaction on the bottom. And over here we have a clockwise magnetic field with an interaction on the top, which now means that our position over here, there's a force down, and a position over here, there's a force up. However, this now causes an opposite motion, which causes the motors to simply, in this position, move this way, and in this position, move this way, which will simply give it an effect that it moves between two positions and does not rotate fully. Now you would see that this motor does not work as spinning does not happen. There's no full rotation 360 degrees. Now in order to get over that, we use a split ring commutator. This resets the current at 90 degrees to stop the motor from reversing. So our current will always be flowing towards us on the right over here and always away from us on the left, causing 360 degree revolutions in the motor. So this would be your negative side of your split ring and your positive, and therefore when we have a full 180 degree rotation, we will always have our current flowing towards us on the right and flowing away from us on the left. So our current, as we've said, changes in A and B to continue our motion. And in that way we get 360 degree rotation in our electric motor, and therefore we get a transfer from electric energy to mechanical energy, which we desire from an electric motor.